Okay, so thanks for everybody to join in to the talk. Welcome. So just as a quick introduction sort of about myself, I'm a computational biologist by training, so I've got a master's in computational biology. I have a PhD in microbiology. I'm a Samba Team member for quite a number of years now, but sort of due to my passion for microbiology, I love to have Samba on small things. So this is a couple of years back. My Samba cluster in a briefcase demo that was really, really nice to build. Was not that nice to fly with, but sort of for running it actually was really fun. Yeah, so that's what I sort of usually do, but as you've seen on the other picture before, I now have Samba on another small thing that keeps me rather busy, so I didn't have time to play with any embedded things this time around. But what I'm going to do is I'm going to talk a bit about Rust. And if you've been here the previous years, you will have heard some of this before, but I'll just quickly get into this for everybody who has missed the previous talks. I'm going to show a little example project of what I was doing with the whole thing and look into the challenges and then sort of sum up with what I think about this. So let's get started with a quick Rust intro, and I guess like the main reason you might be asking is sort of why are we talking about Rust anyway? And I blame Jeremy on this one. So back at sambaXP 2016, he said the Samba project does need to consider the use of other safer languages. He was talking about security issues there. And I mean, Rust is one of the languages that promises or like tries to solve this problem, or at least sort of make it a bit less bad than C is, which is a low bar. But I mean, we can take any help we can get, right? So I mean, the question is honestly, why, right? And like the idea is to avoid whole classes of bugs that you run into if you write C code that by the overall design of the Rust programming language, the compiler will stop you from doing, right? So basically, there's no null pointers in Rust. So you can't have null pointer accesses that sort of screw up your stuff and all sorts of things. So it's a new language. It has a bunch of really nice new features. The Rust compiler, hands down, has the best error messages I've ever seen from a compiler. And I mean, you can see in sort of more recent versions of Clang and GCC that they're sort of trying to catch up a little in sort of also giving better compiler errors and sort of coloring some output to make it easier to see stuff and everything. But Rust still wins hands down. Rust even has some funky features like there's a funky Unicode character that looks exactly like the semicolon. And like a fun troll for your colleagues is to sort of do a search and replace that replaces all the semicolons in their code with this Unicode character because it's impossible to see. The Rust compiler will say, you've got this character here that looks like a semicolon. It's not a semicolon. You want to use a semicolon instead, right? So I mean, I think this is very, very much of an edge case, but I feel like that's the level of error messages you can get from the Rust compiler. It's sort of like you're doing this where you're sort of trying to reuse memory that you were using over here before. It looks like this could be safe. If you're sure it's safe, put it in an extra block here, and everything will be fine. So it actually tells you what you need to do to your code in order to make stuff work. Or it's saying like, you want to be using a mutable borrow here instead of an immutable borrow, right? Because you're obviously doing it wrong, stupid programmer. And all of these really new features that come with it are really, really nice. Another problem that sort of comes up again and again also at these conferences here, it's getting really hard to find C programmers these days because none of the cool kids learn C anymore. And so the next question obviously is, I talked about this before, so why do I talk about the whole thing again? And I guess like the main reason is last time around I fell into like a memory allocation rabbit hole for the project, and like the solution I presented for memory allocation wasn't really the popular choice afterwards. And I'll get sort of into more details on this in a bit. But this is sort of why this year's talk is called like the allocator strikes back, because I'm going to talk about memory allocation on the Rust to C interface all over again. So quick thing about Rust. It's a pretty new programming language. It was sort of announced in 2010. So it's been around for less than 10 years now. It's a C-like compiled language, so if you know C, Rust doesn't feel too terribly different. I mean, the syntax is a bit different, but not too much. There's a strong focus on memory safety, both in sort of making your code more thread safe, but also, of course, trying to avoid like buffer under and overflows and null pointer accesses and all of that sort of stuff. There's like good and bad things with sort of having a package management tool that comes with the ecosystem called Cargo. We can go into a bit of a rant how hard it is to integrate like anything else with Cargo, but on the other hand, at least there's a standard way of getting your dependencies. And so if you're working on a Rust-only project, it's actually pretty decent compared to you have any library in C, and then you need to figure out how to get that one set up with your particular build system thing. And if you use the wrong version of autoconf, good luck with that, right? And stuff like that. So I think overall, for pure Rust projects, it's clearly a benefit. For interop stuff with other programming languages might be a bit of a challenge. It's still a bit of a moving target, so like every once in a while I want to do something in Rust, and I come across a really cool looking library, and they're like, yeah, you can use this, but you need to use like the development version of the language with the latest nightly builds. And I mean, for a development project just for fun, sure. For something I want to do in production and sort of need to maintain for the next 5 years, maybe not so much, but I mean, it's getting there. I think like more and more of the features that you need for a lot of things actually end up in a stable release, and then you can actually start using them. And of course, like one of the things that's also really nice is like the programmers of Rust call themselves Rustaceans. And I mean, I've yet to find C programmers who come up with a really cute name for like the group of C programmers. So I mean, that's a clear benefit of Rust here. And of course, I mean, you can't talk about a programming language without doing a hello world. So here's hello world in Rust. You can see it's pretty straightforward. I mean, compared to Java, where sort of my screen size wouldn't be large enough anyway. And sort of with that, let's have a quick look at the example project. So this is the reason why the talk is called Fancy Talk, because sort of for the project last time, I needed to have like a small toy protocol that I dubbed Fancy Talk that sort of emulates a bit like a more complex protocol like DNS. I've got a parser that's built in Rust for this, so there's a parsing library in Rust, and that is built as a shared library, so I can load it from a C program and actually sort of hand over the parsing of the network package to Rust. And this is sort of what the protocol looks like. So like if you've ever seen like any of the DNS specs, this will look very similar, right? It comes with an ID field. It has a couple of bit flags that you can set that sort of affect how the text that's being sent around is rendered. There's like a 3 bytes worth of color code that you can set for the message, because I mean it's a fancy talk protocol. You can like color stuff, and it's basically you can send a query, and it will return like a payload in response of that query if you talk to the server. So I mean, again, if you have a bit of an idea of how DNS works, it looks suspiciously similar. And like the protocol sort of works by the client sending a query with like a given random ID, and then the server looks up the query in the database and finds like the appropriate response to that, and responds with a payload that fits to the query and uses these bit flags to set up the formatting and fancy colors and everything like that. So let's do a quick demo of like the pure Rust version of this. So basically, if I'm in the server thing, I basically just say cargo run, and my server starts up, and then I can say run Rust, and if I say run Rust hello, oh, nice, it says not found because, of course, it's greeting, sorry. So, but now we've already tried 2 responses from the server. So basically, if it finds something in the database, it sort of responds with the appropriate response. And otherwise, it says, well, not found. And you can also see it does fancy things. So the not found is in bold and red. And like the response to the greeting is in orange and italics. And sort of, I think my terminal doesn't do blink, but I had some answer that sort of also was blinking, but I guess I still miss the blink tag from like HTML of old. But in any case, so it's pretty straightforward, as you can see, so that's how the protocol works. But the Rust server really just was my proof of concept to make sure that sort of both the deserialization and serialization of the package using the library actually worked. The real goal, of course, is implementing this in a C program. So just to show a bit of code here, I know I ended up in the sort of more project-focused track here, and I'm showing slides of code, but sort of just bear with me for a bit. So again, if you know C, you probably have a good idea of what the struct I'm defining here is going to look like. So I basically have a struct that sets up ID, message type, and everything else that is sort of you need to know related to a package in this conversation. And like the message type is an enum that basically says, am I a query or am I a response? And then I can like write a Rust client, and I've left out the network communication here because that's sort of just a bit of extra noise in the slides. But basically what I'm doing at the top here is I'm setting up my package. I'm reading like the query from the command line as I just did in my demo, right? I put like greeting on the command line, so that comes in via my config parsing. I'm encoding the query and write that sort of into a buffer here. And then sort of I need to send this to the network, wait for a response. I get my response back. I dump that in a decoder. And then I parse this again into a package, and then sort of I need to deal with printing it in the right color and everything like that. And so for the Rust server, it's also pretty simple, right? I'm basically, this is the main event loop of the server, and up there, sort of I cut out the actual network parsing that is involved in reading a package from the network in Rust. But basically what I'm doing is sort of the other way around. I'm decoding the package that's coming in. I have my lookup here where I look up the message, like the query in the database, figure out what my response should look like, and then I'm putting this back into a buffer, and that I can send out via the network interface here. One thing you might notice is I have this sort of random extra block here in the code, and it's not actually random. This is sort of part of how Rust handles the memory safety here, because up here I'm sort of passing my message to another function, and then it's down here. So I'm actually using this outbuff, and I'm passing it to the encoder, right? Because the encoder now needs to go and write something into the buffer. And down here, I actually also want to like have the network sending function print stuff on the network that is in the buffer. But basically what Rust says is, you've already given write access to this piece of memory, to this function. I can't just go ahead and give read access to the same memory to another function, because if that function sort of actually is sort of async thread thing that runs off and keeps writing to the buffer, you don't know what the state of the memory is in by the time you send it to the write function. And basically by putting this in an extra block here, I can guarantee that sort of like the write access that's happening is just happening within this block, and sort of Rust is free to sort of give read access to the same variable somewhere later in the code. So this is sort of the only thing that you wouldn't expect as a plain C programmer, because I mean, you know the encoder sort of stops doing its thing after here, and you know it would be safe to do this anyway. So like the C server concept looks very similar. I mean, I sort of call decode package, which is sort of the Rust library providing this for me. I have my business logic in C, so looking up the message in the database is sort of the service that I do. So basically, in a Samba context where we would do the network parsing in Rust, this would be like everything Samba does in this function here, and then sort of we go back and sort of tell the Rust library sort of encode the package, and then we send it off again. And so the shared API also looks very easy. And like last year, I had a bit of a problem that I needed to write this manually. Now a tool called cbindgen has come around that basically can read your Rust code and then sort of automatically generate the header files for you, and does this very nicely. So now, one of the problems with this API here is, sort of, I do like a decode package call here that gives back a pointer to a package. Obviously, that needs some memory that's being allocated on the heap. And so now the question is, who owns the package that I've just allocated? right? And there's two options really. So option one is Rust owns the package because it allocated the memory, and then sort of Rust is responsible for freeing it again. Option two is C owns the package. So I call this, and then sort of I get the ownership of that memory, and now like C is responsible for freeing this. And so for the option Rust owns the memory, right? I just said that. So Rust handles the memory allocation. C just uses the structs and doesn't do anything with it. And then when C is done, it sort of needs to handle, let Rust handle the deallocation again. So basically that means we have a callback free function that sort of comes in to allow Rust to free the memory. Right? So basically our API turns into this. So we have like the decode package, encode package that we had before, and now we also have a free package and a free buffer function. And I mean, that's all pretty nice, but I mean, the thing with free functions is eventually somebody will forget to call it, right? And then you have a memory leak. And I've been in Twitter discussions with people working at like these newfangled internet-y startups who are telling me that they can't stop pushing packages over Christmas because they can't guarantee their infrastructure will survive not being restarted at least once a week. And I found this really interesting because they were like, yeah, you could have memory leaks. And I was thinking, I know of Samba servers that have not been restarted for years, and they just don't leak memory. Maybe it's possible to engineer it that way, I don't know. But so anyway, you will get memory leaks if somebody forgets to call like the right free function at some point, right? And I mean, knowing programmers, it's a question of when, not if. So last year I went with like the other option because I mean that sounded way cooler, right? C owns the memory. So basically, we need to be able to pass back the ownership of the memory to C. And the idea would be then C takes care of freeing the memory, and how can we do this? Well, somehow Rust needs to hand this back. And the idea is we have this cool Tallock library with this hierarchical memory allocation. And so we just need to teach Rust how to also use Tallock for memory allocation, and then we're good, right? We basically just pass in a Tallock context to Rust, and then Rust just puts the memory on there, and then we call like Tallock free in C, and everything's peachy. And that's sort of where the rabbit hole started, because I was like, yeah, okay, so I basically just need to port the C library Tallock to Rust then, and sort of make Rust aware of like using Tallock, and then I need to re-implement like the box and the vec memory handlers in Rust based on Tallock with like the same API and everything. And yeah, I mean, like that was a big can of worms to open there, and sort of I played with this a bit, and in the end, sort of I was sort of presenting that as a like solution of where we would want to go in the talk, and then basically people were like, nah, let's not do this. Like maybe, actually there's obviously a bug here, so it should say maybe let Rust handle the memory after all, right? So let's get back to this. And this is sort of where my talk this year comes in. So let's stay with Rust owns the memory that it allocated, right? So everybody who allocates some memory keeps ownership of that and is responsible for freeing that again, because it's much, much easier to reason about any of this. And the idea is, how can we avoid people sort of screwing up calling the free functions? Well, fortunately, Tallock has another thing that can help us here, and that is it has destructors. So we can just use a Tallock destructor, and we set up like the overall infrastructure. So when you allocate something, you set up the destructor, and then when sort of like a bit of Tallock memory that belongs to a transaction or something like that gets destroyed, that destructor goes off and calls the appropriate free functions. So basically that meant that my C server that sort of like was written using malloc for last year, sort of looking like this, needed to be ported to Tallock in the first place. So basically the port looks a bit like this. And this is sort of still calling free function explicitly. So you can see sort of I'm doing the allocation up here with Tallock. I do the decode package. I get back, like do my response and so on. And then sort of I have a done part where I'm sort of freeing my memory context in Tallock and then free the package, free the buffer. So again, this would be sort of if I forgot a go to done in here somewhere and sort of just did a continue instead, I would still be leaking memory, right? So this is not using the destructors yet. So let's set up the destructors for this piece of code instead. So I think the nicest way to do this is to like set up another piece of memory structure that keeps everything together. So Samba code has a lot of this also in the asynchronous code that people write. Is basically there's a context for whatever particular piece of logic that you want to do, and then basically all the functions involved sort of take this context struct to keep state. So here we basically have a server context that has the pointer to the package, has the buffer, and the way I sort of need to free the memory on the Rust side of things, I'm actually also keeping the buffling, because then I don't have to deal with C strings that are null terminated, and I can't trust that they're null terminated in Rust. And then my free function basically just says, well, if there's a query, free the query, and if there's a buffer, free the buffer. Right? And then in my code, I can actually, I guess, just highlight that. Basically, the only thing that changes is up here, sort of, I'm setting up a new sort of session-related context, and I set a destructor for that. And I mean, obviously, for real code, not a demo, you probably would want to hide this in a function to make sure this always gets called together, because otherwise, obviously, if you forget to set up the destructor, you're still leaking memory. But you could make this a function to set up a server context, and then you would be good. And then sort of, in the end, because that didn't change, it's not highlighted, but sort of I'm just freeing the server context down here, and that will sort of magically fire the destructor that then sort of goes ahead and frees all the memory that I need to free, right? And I mean, this potentially could still leak memory if I forget this part. So still, if I do a continue here and not a goto, I'm still leaking memory. But in principle, for actual code, this probably would be on some further level that might at some point actually also get destroyed by some higher up level Tallock hierarchy. So let's run this again. Oops. In the demo now, and let's have a look at that. So basically, the C server is also pretty straightforward. I'm setting up an LD library path here in order to sort of get this done for the demo. Obviously, for a real setup, you would want this to be somewhere in your usual path. And then I can just change this to run Rust C. And it's also sort of responding with a hello world and so on. But I guess the interesting part, and let me just kill this again. So if I run this in a Valgrind instead, so just to make sure that I'm really not leaking memory. So if I'm running sort of a special message that actually causes the server to quit, because if I just control C out of it, of course, Valgrind will complain about memory not being freed, because I'm not calling the Tallock logic on a sigint. But basically here in the end, you can see sort of there's no, all heap blocks were free, no leaks are possible, so we're good. Right? So this is some pattern that you can actually use. Now, oops. This still relies on a couple of things to be right. So it's not a panacea. We can't sort of just say, let's just use Rust, and all of our memory problems will go away. So the reason I have a make option to run the thing in Valgrind was that I did leak memory in the beginning, right? Because while writing the Rust-free function, I actually did stuff the wrong way. So Rust is really, really good at making sure that you're not leaking memory in pure Rust code. Sort of every time you hit this foreign function interface layer, things get a bit sort of more wonky, and a lot of the Rust guarantees actually don't apply any longer. So basically, there can be null pointers. Memory allocation is something you actually need to take care of, and sort of there's unfree blocks all over the place, unsafe blocks all over the place to tell the compilers of yeah, I know potentially stuff in here could fail, and you can't validate that everything is correct because sort of you don't know what everybody else is passing in here. But trust me, I wrote this correctly, right? And I guess ideally the nicest way of doing this with sort of the highest level of paranoia here would be to have an opaque object that I'm sort of getting back from the library, just as sort of a fancy talk library context thing, and I'm sort of just keep passing this around back into Rust for everything that Rust does, and then have wrapper functions for all the accesses to the struct. Right? That's not what I did in my version, because that then requires to write a lot of access functions. So you basically need getters and setters for everything. But of course, again, in the Samba case, we would be auto-generating a lot of the Tallock code from like PIDL or something like that. So I guess that wouldn't be too much of an issue. So basically, sort of coming up to the conclusions, actually, not sure how I'm doing for time, decently. I think like the big challenge, so we had a bit of discussion like 2 days ago over a couple of beers, and probably could have spent more beers discussing this even longer, or maybe at least just ranting about this a bit longer, is sort of how to integrate build systems, right? Because on one hand, Rust's cargo build system is very opinionated on how the world should work like. And if it's not in charge of everything, it gets really unhappy. On the other hand, the Samba build system, sort of WAF Samba, is also rather opinionated about things. And it's very special because like we are the only project on the planet that actually uses it. And I mean, it's sort of similar to sort of upstream WAF, but it comes with a lot of extra logic that we've sort of plugged on top of it that doesn't necessarily make it easier to understand. And I'm not even sure how many sort of other larger projects are still using WAF. I know Node.js was using WAF at some point in history, but they've long switched away from it. So as opposed to a lot of other build systems that are sort of more common, if you run into an issue with WAF, you're basically on your own. So like sitting down and figuring out all of that is not necessarily what I would consider fun, which is also why I've avoided doing this for my little toy examples here. So that's a bit of a problem. So the other problem is sort of always, from a Samba perspective, there's a bunch of people around who insist that sort of if we ship Samba, it needs to build on some ancient AIX or whatever HPUX machine that I don't know was last updated in 1993 or something like that, and still needs to work. So I mean, we had this fun trying to build a lot of our system administration and scripty stuff in Python. I still remember like the big discussion we had until we came up with an option of saying, hey, we actually have a configure option that says, well, you can sort of ignore Python for this build, or sort of like we ship an extra Python tarball along with Samba, and then we sort of build the Python version that Samba can use along with Samba and stuff like that. And we'd have to figure out how to do this with Rust as well, if we have Rust libraries that we depend on, right? I mean, if we can sort of completely separate them, might be doable, but sort of, I mean, this is something we need to consider, right? So basically, if you do like a git clone of Samba, you then would get like a code that is C, code that is Rust, code that is Python, code that is Perl. So it sort of just adds to the Tower of Babel that is the Samba project. So that's also a bit of a problem. It might be worth it still, but something to consider. I would like to say that the Rust community as such is really super helpful. So I mean, I was struggling with a bunch of the sort of more intricate details of the foreign function interface and just how to handle memory safety and making sure that I'm not leaking memory all over the place. And the Rust documentation necessarily, like especially for the foreign function interface, is not great. They basically just come with some toy examples that really don't care about memory that much. So basically it's just passing stack allocated stuff around, like ints and things. But the Rust community is really super helpful. So I was on IRC and their Discord server, and basically getting help for this sort of stuff is really, really nice. So shout out to some people who really helped me a lot there. But I mean, overall, sort of it's a very friendly community. I think that's something a couple of other open source projects could try to emulate a bit more. So basically, obvious future work would be sort of trying to figure out how we can auto-generate a lot of this code from idle as a baseline. Because the way Samba does this at the moment is we have this Perl program PIDL that takes the IDL files and auto-generates C code. And then for a lot of the protocols, you need to do some extra stuff on top of that PIDL can't auto-generate, and that you write in C. And the idea would be to sort of auto-generate all the easy stuff from the idle files for Rust, and then sort of you write some Rust code on top of that, and that's then hopefully going to be safer than the C code that you'd write manually, right? But sort of this is something you would have to look into. And then, of course, there's the build system integration, and sort of like unhappy smiley is there for a reason, because, I mean, like build systems, I actually like build systems that I don't need to touch. So it's really not something I would look forward to doing. But I mean, in the end of the day, you would have to do this. So, and with that, I'm sort of at the end of my talk. And any questions, comments, like angry rants about programming languages, please go ahead now.
So with the memory allocator, now, in a normal C program, you'd have to go through all of the fun stuff that you've just gone through. Now, but using Tallock, did you consider replacing the Rust system allocator with Tallock so that anything returned from the foreign function interface could then just be reparented into the Tallock context inside of the Samba side?
So that I didn't look at. That possibly would also be an option. I still think from like to keep the sort of look and feel of writing Samba code, it would be nicer if you could actually pass Tallock pointers around, right? Because, I mean, a lot of, so basically, if you look at the function signature of most Samba functions, they'll start with like a Tallock context pointer, right? And that's, I feel like what the natural flow of writing Samba code is, right? And I think it would be nice if I could just call, like going back to one of the source code examples, right? If I could just go and say like decode package Tallock context in buff. Oh, so I guess I would pass the server context here to get my Tallock context in, right? And that would just feel natural to a Samba developer.
An option there could be that everything that all of the system types that you would get, anything that's a ref in Rust can be cast into a star const. Then, because you're allocating that from Tallock, you could then have inside of the Rust code, then associate that with any other star ref you've just taken in, which itself came from Tallock. And then that way you wouldn't have to redo too much in terms of the box vex stuff.
Yeah.
So that could be an option.
I think this is also worth looking at. So mainly this time around, people really sort of at the last time I gave the talk, so last year, we had a sort of larger discussion after the talk, and people generally were in favor of sort of using the every language keeps track of its own memory stuff and then sort of just is responsible for freeing that. But no, I agree. So I mean, like there's a couple of options. I think like the nice thing about sort of both of like using the Tallock destructor setup or sort of using Tallock as a sort of the allocator library in Rust, is Tallock is really nice and powerful, and you can do a lot of really fun things with it. And so it gives you that flexibility. I mean, at the end of the day, I think it's worth building all of these different options and then sort of looking at which of these actually feel nicest to use when writing code, right? Because at the end of the day, if it's like really annoying, clumsy code to write, nobody's going to use it, and people will keep writing their like network parsing layers in C. And I guess like at the end of the day, that's what we want to stop.
I hope that question is not too stupid, but since most people who would write Rust are familiar with an C background, which is like the complete opposite with non-functional concepts. Since we are losing most of the promises we get from the Rust compiler whenever we are using unsafe code, I don't get where the big upside is in actually using it, since C programmers will rewrite C-ish code and
so
the larger concept I'm missing.
So this is something I, of course, also thought about quite a bit, right? Because, I mean, at the end of the day, if sort of using the foreign function interface means that most of your code is within unsafe blocks or unsafe functions, then what's the point of writing Rust code in the first place? But this is really the interface layer only, right? So you can make sure that your interface function makes sure that whatever is coming in is actually good and safe. And then you can still do like the parsing and sort of serialization and deserialization in Rust. And you can use a library like Serde or something like that that's sort of really powerful, really nice to use, widely used already for a lot of things that sort of people have looked at. So, I mean, it's pretty good confidence that this is sort of not less safe than other things that people are using, right? So the idea is, and I think this is, I have never used a larger scale Rust project, but I think for most things you do, at some point you'll have to interface with the outside world that is not Rust. So it's probably impossible to write a larger Rust project without any unsafe code whatsoever. But the idea is to have as little of your code base as possible in the unsafe blocks, right? Because the unsafe blocks are basically the same as C. So at the moment, when we write C, the way we make sure that the code is safe is we stare at it very hard and try to be smart about it, right? And as we've heard before, it's a stupid idea to sort of rely on staring at code for anything. And so like Aurélien had like a nice rant on that part, right? I mean, for debugging, but I mean, for making sure your code is correct, it's the same thing. And if we can sort of reduce the amount of code that we need to look at and be smart about, that's already a win, right? So even if it doesn't get you all the way, it will still make a lot of the code safer. And I think, like, if we look at the current fad of fuzzing network interfaces and like how successful it is in finding bugs in the parsing layers, right? I feel like we can need every help we can get on the parsing level. And if we can make that in Rust, then if the interface to where C stuff comes in, and sort of we can still crash if somebody puts in a stupid pointer from C or something like that, right? But that's not different to the C level. But like, hopefully we can at least make sure that nothing that comes in from the network side of things blows us up.
Do you mind if I also answer this?
Sure.
So I've done a lot of C, Rust, foreign function interface stuff as well, and I don't know if it's on a larger scale or not, but I think one of the important things to consider in this is that Rust is actually two programming languages. There is safe Rust, which is all the Rust that you normally touch, and then there is unsafe Rust. Now, unsafe Rust has to do a lot more checking of things. Now, unsafe Rust is not that much different to safe Rust. There's only two things that you can do differently. One of them is dereferencing pointers. The other one is calling more unsafe code. So what Kai is kind of trying to say is that if you're coding in C, all of C is unsafe C. Whereas if you're doing Rust with a foreign function interface, you've got, here is a thin layer of unsafe, which is allowed to do dereferencing, and then all of the rest has a number of assertions which still exist. And even unsafe Rust still has very strong assertions that do not exist in C. So you can write Rust in safe Rust in a C style, but you will never have the blow-ups that exist from like C. So you can turn off, you can ignore all the functional stuff, you can just do point like references and lifetime and all of that stuff, all in safe Rust, and you'll never have the blow-ups that happen in C because you're still in safe Rust. It's only that thin unsafe layer where you can do the dereferencing that becomes a problem, and now you can have stricter auditing. You can actually grep through your code and say, where is the unsafe? And you can say, here is where we need stronger assertions about our correctness. And that's where we can get better confidence to be able to say, yeah, these are the only parts where things can go wrong. Whereas in a C program, the entire thing is a giant, potential risk where all of it could be dangerous. So a really good example is if you've got a function that calls another function, they each pass a pointer. Where do you check if the pointer was null? Well, you've got to check it in both because you don't know who's calling you. Whereas in Rust, an option type actually compiles to a pointer, but only the first one has to check. Because once you've got an option T, you destructure that to a type T, and then you pass that to the second one can guarantee at compile time that only things that have already done a null pointer check can have passed it to it. So this is the kind of thing where the correct solution in Rust is also the optimal solution, compiles as though it's like C and has, the same performance. So I think it's a bit more subtle than what is advertised, and it's one of those really hard things. The Rust team has a really good document on this called the Rustonomicon, named after the Necronomicon, and it teaches you all of these horrible things about how the language actually works internally, and that could actually be a really good reference for you if you want to learn some more. So sorry to hijack, Kai, I just wanted to help out.
Fair enough. So maybe sort of as part of the answer to, or like as an illustration to what I was saying, right? Is this readable for everybody? Or okay. So basically, if you look at the encode, so this is the Rust library that does so this is the C interface that I'm providing in order to sort of export to the C library. So it's like all extern C encoding, and I'm setting a no mangle, so the function name actually doesn't get mangled in the compiler and everything like that. So I actually know what function to call when I'm linking. And if you look at the decode package, right, the only part of this code that is unsafe, and I mean, like for the sake of the argument, it's actually unsafe and might blow up because I'm not doing the checks, right? But really the only part of it that is unsafe is this part of here, right? So like nothing else, so everything else here is safe Rust, and the only part of Rust that I'm writing that's sort of unsafe Rust is in here. And I mean, obviously for a non-toy example where I sort of wanted to be more defensive about what I'm getting in, I would sort of make sure that whatever is coming in here actually is correct, right? Yeah.
You can actually improve this. Where it says package star const C package, because option guarantees with non-null optimization, you can actually just take in a pub extern C interface, you can actually do option percent C package.
That's true.
Yeah.
I mean, ideally, I also would sort of, so again, this would be what I would do for the like opaque object, because then I sort of could use the same function calls really for C and non-C. But I mean, again, so also if you look at the other thing, like there's one unsafe block here and one unsafe block here for the encode package, and that's everything that's unsafe in here. And yeah, again, right, so I'm being a bit paranoid here, and like using the option type instead would solve that, and I would do like a match instead, or like an if sum or something like that, right? I mean, so you can build this, but sort of there's really not a lot of places where you sort of need to be really careful about things, and they're sort of nicely localized and easy to find, right? So you basically have something in the programming language, namely the unsafe thing, that tells you, look here, this is the part where things can blow up. Everything else, the compiler guarantees, is fine, right? And I feel that that's a big win compared to writing the same thing in C.